Welcome to our tutorial on inner products, lengths, orthogonality, and orthogonal projections. Today, we'll explore these fundamental concepts in linear algebra step by step, focusing on the real vector space Rn. Let's start by understanding what an inner product is. An inner product is a function that takes two vectors and returns a scalar value, satisfying certain properties. An inner product must satisfy three key properties. First, symmetry. The inner product of u and v equals the inner product of v and u. Second, linearity in the first argument. The inner product of a scalar times u plus w with v equals the scalar times the inner product of u and v plus the inner product of w and v. Third, positive definiteness. The inner product of a vector with itself is always non-negative and equals 0 if and only if the vector is the zero vector. The standard inner product in Rn is the dot product, where we multiply corresponding components and sum them up. For example, the inner product of vectors 1, 2, 3, and 4, 5, 6 would be 1 times 4 plus 2 times 5 plus 3 times 6, which equals 32. Once we have an inner product, we can define the length or norm of a vector. The length of a vector v is the square root of the inner product of v with itself. The norm has several important properties. First, the norm is always non-negative and equals 0 if and only if the vector is the zero vector. Second, the norm satisfies homogeneity. The norm of a scalar times a vector equals the absolute value of that scalar times the norm of the vector. Third, we have the triangle inequality. The norm of the sum of two vectors is less than or equal to the sum of their individual norms. Let's visualize the norm in R2. The norm of a vector is simply its length in the usual geometric sense. For example, the norm of the vector 3, 4 is the square root of 3 squared plus 4 squared, which equals 5. Now, let's discuss orthogonality. Two vectors are orthogonal if their inner product equals 0. Geometrically, this means they're perpendicular to each other, forming a 90-degree angle. Moving on to orthogonal sets. A set of vectors is orthogonal if every pair of distinct vectors in the set is orthogonal. If, additionally, each vector has unit length, the set is called orthonormal. Orthonormal bases are particularly useful in linear algebra. If we have an orthonormal basis, we can express any vector in the span in a very simple way. X equals the sum of the inner products of x with each basis vector times that basis vector. Let's now explore orthogonal projections. First, let's look at the projection of a vector onto a line. The projection of a vector x onto the line span by a non-zero vector u is given by this formula. The inner product of x and u divided by the inner product of u with itself, all multiplied by u. Geometrically, the projection represents the shadow of vector x onto the line along vector u. Let's visualize this with an example. Consider the vectors u equals 1, 2, and x equals 3, 1 in R2. To find the projection, we need to compute the inner products. The inner product of x and u is 3 times 1 plus 1 times 2, which equals 5. The inner product of u with itself is 1 squared plus 2 squared, which equals 5. So, the projection coefficient is 5 divided by 5, which equals 1. Therefore, the projection is 1 times 1, 2, which equals 1, 2. Now, let's generalize to projections onto a subspace. If we have a subspace W with an orthonormal basis, the projection of a vector x onto W is the sum of the inner products of x with each basis vector times that basis vector. This projection has a key property. It gives us the unique vector in W that is closest to x. The error, which is x minus the projection, is orthogonal to every vector in the subspace W. Let's visualize the projection onto a subspace in R3. Here, we have a plane as our subspace W, and a vector x in 3D space. The projection of x onto W is the point on the plane closest to x, and the error vector is perpendicular to the plane. Let's summarize what we've learned. First, we define the inner product, which gives us a way to measure how vectors interact with each other. Second, we used the inner product to define the length or norm of a vector. Third, we declared vectors to be orthogonal when their inner product is 0. Fourth, we discussed orthogonal and orthonormal sets, which make coordinate expansions easy. Finally, we learned how to project vectors onto lines or subspaces using inner products and orthonormal bases. These concepts are foundational in linear algebra and have applications in many fields, including computer graphics, machine learning, quantum mechanics, and signal processing. Understanding inner products, orthogonality, and projections provides powerful tools for solving problems in vector spaces. Thank you for watching.